Hello and welcome to Chapter 5. We're going to be talking about what we meant by series connected circuits in DC. And by this time, you should really be very well familiarized with the concept of voltage, current, resistance, and be comfortable using Ohm's law and what Ohm's law means. It's very important that you understand by this point the relationship between voltage and current. We're going to review some of those things as we go along into this chapter, but if you still have issues understanding Ohm's law, I recommend you go back and really review it, because this chapter assumes you really know how to use it and how to implement it. If you have any questions, you can always let me know. So in this chapter, we're going to be looking at the characteristics of what we call series connected circuits and how we can solve for voltage, current, and for power when we have circuits connected in this way. This is one way of connecting circuits. It's not the only way, but it's probably the simplistic way of connecting elements in the circuit. And when we look at series connected circuits, we're also going to be talking about a very important law that is called Kirchhoff's voltage law, and how this applies to the analysis of circuits. And we're also going to be looking at how when we apply a voltage, that voltage can divide among the series components, and how we can apply what is called the voltage divider rule, a very important property of for solving circuits. And we're also going to be introducing some new terminology, some new notation that we call single and double subscript notation, so we can understand voltage levels in a network. And briefly, we're going to talk about how to approach the measuring of voltage and current in a series connected circuit, although we're going to leave those topics about measuring more for the lab when we do some of those hands-on measurements. All right, so let's start by looking at this simple circuit again in this figure, where you have a simple battery connected to a resistor through some wire connection. So very important things to realize here. One is that you have what is called a ground connection. The ground connection is the lowest potential point in your circuit. Okay, so in this case, the ground connection is connected to the negative of the battery, right? And the important thing is that you be able to follow the path for each of the elements in the circuit, right? So if we start with the bottom here, right, where this is the ground symbol, and the ground is connected to the negative of the battery. The positive of the battery then is connected to one end of the wire, and that wire goes through the one connection point in the resistance. And the other connecting point of the resistor, the other lead, goes back to the ground. So what we have here is a complete circuit, a complete path. We cannot have current flowing in a circuit unless we have a complete path like you see here. So a full path must exist for that current to flow. And if you remember, this battery here is what pushes those electrons out of the battery towards the resistance through the connection of the wire. And you notice here that there's two currents indicator, right? We had the normal electron flow of current that we physically more familiar with, right? And that means that electrons coming out of the negative point in the battery are going to be attracted to the positive side, right? So they're going to flow in the counterclockwise direction in this way, going from the negative to the positive. That's electron flow, okay? And you also notice what we already know as conventional current flow. Conventional current flow says that the current is always trying to reach the lowest potential, right? So in this case, this conventional current flow is leaving the positive terminal and is going towards the negative terminal, right? So remember, we're not going to follow electron current flow in this course. We're always going to follow conventional current flow. So make sure that is something that we're comfortable with, understanding. Okay, and we're going to review it again in a few moments. So you have here a complete circuit, right? A circuit that is connecting a battery and a resistor together, and based on that, you can then, find, for example, the current through this resistor by using Ohm's law, which will be the voltage across the resistor divided by the resistance of the resistor, right? And in an ideal situation like this is, we assume that this wire, it doesn't introduce any resistance, right? We assume that the wire has an ideal zero resistance, so the voltage being applied or the voltage being supplied by the battery is exactly the same voltage that you see across this resistance, right? Okay. And so in this case, this voltage here at the battery is exactly the same voltage here across the resistance. So again, one more time here, if you see in this figure, is that you have the direction of current flow, right? If you notice here, this current, as you notice by the arrow, is leaving the positive terminal, right? Because what happens is, as long as you have a connection to the battery, the current is going to keep flowing, right? It's going to keep flowing, flowing, flowing until something happens. Either this device here creates an open and no more current can flow, or the battery dies out, right? And you cannot provide any more electrons for current to flow. But as long as battery and resistance have a permanent connection, then this current is going to keep flowing. It's going to just flow out, back in, out, back in, out, back in, and so forth. If this is a light bulb, that's what you see, right? You'll see light permanently until maybe the battery dies out. So again, this shows you the notation and the symbol for a battery, in this case, a DC source. Normally you have the parallel bars, like in this case, a set of two parallel bars. The large one indicates the positive, the little one indicates the negative. Sometimes you only see one pair of bars, and either notation is fine. And you also see here, in this other figure, you'll see then, from the resistor point of view, the current, how the current is going through the resistance. And again, from the resistance point of view, you can see that the current is going towards the negative end of the voltage, of the polarity, right? So that's the conventional current flow that we always follow. All right. So, so that's really nothing new. We knew that from the previous chapters. We knew this from conventional current flow. We knew this from Ohm's law. And we know this from the relationship between voltage and current, correct? So now let's see what happens if we connect resistors, if we tie resistors in what we call a series connected circuit. And there are a couple ways of understanding what we mean by a series connected resistance. Well, the best example I can give you is if you think of Christmas tree lights, right? It's one string, and you see little lights connecting throughout that string, and there's only one point of common connection between two, right? So two lights, if you think of R1 and R2 as two of those lights, are connected with a single point. R2 and R3 also connected at a single point, right? There's only one single connecting point, as you can see, single common connecting point. So think about it the same way when you look at Christmas tree lights, right? It's a big string of lights, and between any two lights, there's a connecting point in common, right? It's the same idea here. And you'll see the advantages of having series connected resistors later. And this applies later, even more so, will apply later to other type of devices and even to electronic devices later. So the concept is still the same. So in this case, you'll see here that you have three connected resistors, R1, R2, and R3, in series. Now, important again that we realize that they're connected in series because they have one connecting point in common, see? And they form a single string, if you will, right? So from A to B is a single string. And in that single string, there are three resistors connected together. To give you a counterexample here, we'll look at this in more detail in the next chapter, but if you look at figure 5.5, you see a case where the resistors are not in series, because now you have three resistors sharing one single point, okay, right here. So again, for the resistors to be in series, they can only share two resistors can only share one single connecting point. And here you have three resistors sharing the same connecting point. So for reasons that will be more apparent later, in chapter 6, you'll see that they're not connected in series. Okay, so you can think of it as more of a physical visualization of the connecting elements in series, again, by looking back at how Christmas tree lights are connected. So it's important for us in many of these cases to understand what the total resistance is when we have all those resistors connected in series. By total resistance, we mean what will happen if I place a meter. And remember from the lab we did, or the only lab we've done so far, if I want to measure R1, I will simply place the meter across R1, right? From A to this point, I will measure R1. From this point to this point, I will measure R2. From this point to this point, I will measure R3 individually, right? I can do that, no problem. But if I wanted to know what's the total resistance from A to B, so from this point over the left of R1 to this point over the right side of R3, what is the total resistance across the three resistors? Well, that's what we call the total resistance for those three resistors. So if I place a meter, if I place one lead of the meter at A, another lead at B, I will be measuring the total resistance, right? Because the wire has, if it's an ideal wire, it provides no resistance. It's just a connecting point. So the total resistance from A to B is what I call, is what we try to figure out. We can find by, if we measure it by simply connecting an ohm meter from A to B. And that will measure the total resistance. Now mathematically, I can calculate the total resistance, and the formula is very simple. The total resistance for any resistors connected in series is simply the individual addition of each resistance. So the total resistance in this case will be R1 plus R2 plus R3. If you have any number of resistors, N, it's just adding them one by one. So for any number of resistors, the total resistance is just R1 plus R2 plus R3 and so forth until the last resistance. So the more resistors we add in series, the greater the total resistance is, no matter what the individual values are. That's something important to remember, because later you'll see that we're going to be looking at cases in circuits where things may not be always connected in series, and this will give you clues as to how do you determine those things. So it's important to realize that if resistors are connected in series, the total resistance is always greater than any of the individual resistors, okay? The other thing is that the largest resistor in the series combination will have the most impact on the total resistance, okay? Is another nice thing to remember. In other words, in this circuit, in this simple circuit with R1, R2, R3, the 100 ohm is going to have the greatest impact on the overall circuit. Okay, the largest resistance always has the more impact, and we'll see why later. So in this case, simple case here of a 10, a 30, and a 100 ohm resistance, the total resistance is simply 10 plus 30 plus 100 ohms, or 140 ohms for the total resistance. So mathematically, again, I'm just adding the three resistors together. If I put a meter from A to B, I will ideally measure 140 ohms. Another example here, in this case we have 4 resistors. Again, if I want to know what the total resistance is from A to B, looking, another way of saying this, and you'll find that notation in some books, is saying what's the total resistance looking into terminals A and B. Okay, and it comes from the idea that from this, if you put a source across A and B, a battery, let's say, a power supply, from the point of view of the battery doesn't really see individual resistors. The battery will see the total resistance connected to that battery. And so the battery or the source sees a total resistance from the point of view of A and B. That's what it says, looking into those terminals, rather, A and B, the total resistance will be, in this case, the addition of R1, R2, R3, and R4, because they are in series. Now, before I can add them, before I can tell that I can add them together, I need to make sure that they are connected in series, okay? And again, that's one of the things you need to start understanding before you can assume whether they're in series or not. Now, physically here, it's very simple to determine that they are in series, right? Physically, they look like they're connected in series. So it's one single string, right? From A back to B, right? So it's easy to see here. In some cases, it's not that easy to see, especially if you look at a circuit where you have connections that are not as neatly drawn as you see in this figure. But the clues are that, again, you have to have a single connecting point between any two of the resistors. Okay. So in this case, you have that, and it's a single string connecting all those resistors together. So the total resistance is simply the addition of the individual resistor values: 200, 220, 1.2 kiloohms, and 5.6 kiloohms. So the total resistance is equal to 7.04 kiloohms. And remember we said before that in a series connected circuits, the largest resistor is the one that has the most impact. One way of looking at that is that if you look at the total resistance is is really closest to the largest value of the individual resistors, right? The largest value among the individual resistors here is 5.6. So the total resistance is really closer to 5.6 than to any of the other values. You notice that, right? Those are simple things, but are clues later that will help you in analyzing circuits, as you'll see later. So keep those things in mind. They're very important. They're subtle points, but they're very important points. And in the special case where all the resistors are the same, then it's a simple formula. You can just multiply the total number of resistors times the individual resistance. For example, in here you have 4 resistors. Again, they're connected in series for reasons that we already know, right? So you can see, and you should be able to at least physically tell that they're connected in series. And you notice that all the values are the same, 3.3 kiloohms. So for cases where all the resistors have the same values, if you apply the formula, you really all you have to do is add 3.3 plus 3.3 plus 3.3 plus 3.3 4 times, right? Which is equivalent to multiplying 4 times 3.3. So that's what this formula is. If all the resistors are the same, all you have to do is multiply the total number of resistors times the individual resistor value. And this is what this is. So in this case, it's 4 times 3.3 or 13.2 kiloohms. Okay. Another thing to notice is that from this point of view, from the point of view of this connecting point A and B, it doesn't matter if you change the locations of the resistors. If you swap them, the total resistance is not going to change. In other words, if I swap the position of R3 and R1, if I swap them, and if I swap the positions of R2 and R4, the total resistance is not going to change. Okay, it doesn't matter what I swap. Now, it's going to matter from your circuit point of view. It's going to matter because, think of, for example, if you have lights in a house, this R1 may represent some light in the living room. This R2 may represent some light in the kitchen, and so forth, right? So physically, it's going to matter, obviously, where you put them. But electrically, looking at the connecting points from A to B, the total resistance is not going to change, okay, if you swap them. So again, the total resistance of resistors is unaffected in a series connected circuit, and important, in a series connected circuit is unaffected by the order in which they are connected. Another quick example here, you see 30 plus 82 plus 10. We swap the resistors here in this second figure, and as you can see, the total resistance is not going to change. It's going to remain the same. Okay. Another example here, it says find the resistance for this series connected circuit of resistors. Okay. In this case, we happen to have 3 resistors of the same value. So we could, if we want, just connect those or partially add those 3 together using the formula that we talked about before for same value resistances. So it'll be 3 times 1, right? So this is n times R2, R2 being 1 in each of those, in R3 and R4 and R5, right? So it'll simply be R1 plus R3 plus n times the other 3 resistors, n times being 3 because you have 3 of the same. So you have 4.7 plus 2.2 plus 3 times 1, all K values gives you 9.9 kilo ohms. Okay? So again, and if I redraw the circuit, like if you look at figure 5B and 510, the total resistance is going to be the same. It's not going to change anything. Okay? And again, the fact that these resistors in figure 5.9, R2 and R4 are not directly connected, it doesn't mean that I cannot combine them. I can combine them as well, whether they're connected, like look at figure 510, how all the 1Ks are connected in next to each other. And in 5.9, they are not connected next to each other. That doesn't matter because I can swap the positions and the total resistance is not going to change. Again, physically it may change because of positions in different parts of your circuit, but as a whole, as a total, the total resistance is not going to be affected. Later in the lab, we're going to be looking at some of these cases where you measure. In this case, like I told you before in the previous example, if you wanted to measure the total resistance for these 3 resistors using a voltmeter, ohm meter, you will put the leads of the voltmeter across the 2 endpoints, and you will then measure the total resistance, okay? Which in this case is 140 ohms. All right, so now we understand how to handle series connected circuits, right? We simply add them together. So now we're going to be looking at what happens when we form a circuit with series connected resistances, right? By forming a circuit, we mean we have a complete path. We had a battery and we complete the path, right? It's important, right? Because completing the path is what allows current to flow. If the path is not completed, is not terminated, there's no current flowing in the circuit, right? We have to have that complete path. So in this case, we'll say that a circuit is any combination of elements that result in a continuous flow of charge or current through the configuration. So in this case, once we connect the battery, right, to these 3 resistors through a ground, then we'll have current flowing in the circuit. And the current here is, again, conventional current flowing through each of the resistors, R1, R2, and R3, right? And again, going back to the source, out of the source, through the resistors, back to the source, and so forth, right? And so that this DC supply, this battery, whatever it may be, it's also a two-terminal device with 2 points connected. Again, remember that polarity is really critical when you look at batteries. So you have to be aware what the polarity is and how the connections are to the polarities in the battery. So for this series connected circuit, the direction of conventional current flow is such that it's going to leave the positive terminal of the supply and it's going to return to the negative terminal. Okay, leaves the positive terminal, returns to the negative terminal. That's the direction of conventional current flow. Another way of saying this is that that's the direction of positive current. Okay, the direction of positive current is leaving the positive terminal towards the negative terminal. Okay, negative current exists. Okay, if we swap that direction, the current becomes negative. Okay, that's not that's not impossible. It can happen. But what we should understand is that going from positive towards negative indicates a positive current flow. It's very important, and I mentioned this several times before. You have to be aware of the polarity in the voltage, and you have to always be aware of the direction for a current. Okay, the values of voltage by themselves are not that doesn't give you the whole picture. The value of current by itself doesn't give you the whole picture. You have to know the polarity of the voltage, and you have to know the direction of the current, because that will determine many other things. Okay. All right. Another way then of saying that circuits are connected in series is that the current is the same throughout the circuit. In other words, if I measure the current right out of the battery, it'll be the same current that I will measure between R1 and R2. It will be the same current that I will measure between R2 and R3. It's the same current. Even if I measure the current going through this wire, it's just the same current. The current doesn't change, ideally, assuming these connections are ideal. So in a series connected circuit, the current is the same at every point in the series circuit. It's a very important rule. Remember that. The current is the same at every point. So in any configuration, if two elements are in series, the current must be the same. However, if the current is the same for two adjoining elements, they may or may not be in series. That would become more apparent later. Okay, if you don't understand that statement yet, don't worry about it. It'll make more sense later. But just remember that by default, if you determine that resistors are connected in series, that you can safely assume that the currents are going to be the same through the resistors. Okay. However, if you're told that the current is the same through some of those resistors, it doesn't mean they may be connected automatically in series. Okay, it goes one way but not the other. If you already know ahead of time that the elements are connected in series, then by default the currents will be the same. Okay, but not the other way back. All right. So now, and again, we'll look at ways later of making a more clear concept. But for now, just remember that assumption for elements connected in series. If you know their elements are connected in series, then the currents must be the same. So again, we can apply Ohm's law to this circuit, so just like we did with individual resistors when we looked at simple circuits, even if we have more than one series resistance. And in this case, it's what I already said before. If you look at terminals A, B, another way of saying the total, what's the total resistance is saying what is the total resistance looking into the terminals A and B. Because from the source point of view, the source only sees the total resistance. It doesn't see, in quotes, the individual resistors. Okay, this from the from the battery point of view, from the source point of view, it sees this blue box, okay, which represents the total resistance of 140 ohms. Okay, so in this previous circuit, then, if you want to know what the source current is, the current coming out of the source, okay, one way of knowing that is by using Ohm's law. And you know the Ohm's law says that the current is going to be the voltage divided by the resistance in the circuit. So in this circuit, the voltage being supplied is 8.4 volts. But the total resistance is the resistance you need to calculate that current. In this case, the total resistance is 140 ohms. So the total, or the current will be 60 milliamps. So in this case, again, for you to know the total current or the source current flowing here, you have to use the total resistance, not the individual resistance, okay? The total resistance. The polarity of the voltage across the resistor is also determined by the direction of the current. Remember, this is something I talked about before in relation to conventional current flow, but it's again important that you review this. And there's two ways of looking at this, right? If you know the polarity of the voltage across the resistor, right? If you already know that, then automatically you should know the direction of the current. Why? Because if you know, for instance, here that this is the positive end and this is the negative end, conventional current flow, positive current will always flow towards the negative side, towards the negative point of the voltage, right? So then you know this is the direction of the current. The same thing here. If this is deemed the positive terminal and this is deemed the negative terminal, current is going to go towards the left in this second case, towards the negative. And it doesn't matter how you draw the circuit or the resistance, right? Again, what you look for is the polarity. If this is the positive end and this is the negative end, current is going to go up in this case, up in this direction, towards the negative, towards the negative, towards the negative, towards the negative. And it's also important that you understand. So what I was just explaining here is based on me knowing or you knowing the polarity. If I know the polarity, I know the direction of the current, and you should be able to deduct that from the figures. You should be able to figure that out. That given these polarities, those three polarities, you should come up with the direction of the current. The other way around, or the other way of looking at this also, which is important, is that if I know the direction of the current, I should know the polarity of the voltage, and they should both check. So if I know that the current is going in this direction from left to right in this figure A, then I automatically know that the polarity at the left is positive, and at the right is negative. This direction gives me this polarity. This polarity gives me this direction. Okay? So I will urge you to really, really understand the three cases here and be able to determine polarity from direction of current and direction of current from the polarity. Make sure you understand that. That's a very subtle thing, but it can create a lot of confusion when you look at more complicated circuits where it's not that obvious where things are connected or how things are connected. But if you keep up with this notation and with this terminology, there's no way you can go wrong. So you have to really understand these simple cases and how to get one from the other. Okay. And so if you want to calculate or figure out the magnitude of the voltage across each resistor, then you can simply use Ohm's law for each of the cases. It doesn't matter how many resistors you have in the circuit. So for example, if you look at figure 512 again, the one we just did where we calculated the total current in the circuit, if you want to know the individual voltage drops across resistors R1, R2, and R3, we can reuse Ohm's law. Okay? So if I want to know what V1 is, using Ohm's law, I know that V1 is going to be equal to the current across R1 times the value of R1, right? That's very important. The voltage across, or the voltage across R2, the voltage drop across R2, and it's a drop because it goes from positive to negative, okay? That's what we call a drop. And again, this is all relative, okay? Because if you go from left to right, is a voltage drop. But if you go from right to left, is a voltage gain. This is the same idea as if you're standing up on top of two hills and one is taller than the other one, right? If the hill at point A is taller than the hill at point B, if you go from A to B, you go down. But if you go from B to A, you go up, right? It's all relative. So that's what this indicates in here. But in any case, looking at this circuit and looking at the direction of the current is flowing, we see that V1, there's a drop from across this resistor R1, there's a drop across resistor R2, and a drop across resistor R3. And I can calculate those voltage drop by simply using Ohm's law. So V1 is simply I1 R1, V2 is I2 R2, and V3 is I3 R3. Now, what happens is that, as we mentioned before, if we're looking at a series connected circuit, this I1, this I2, and this I3 is the same because the current is the same throughout the series connected resistors. It doesn't change. It's the same current. So the only thing that's different is the value of resistance, right? So the voltage drop is going to be equal to that current, which is 60 milliamps, times the individual resistor. So you have for V1, you have 0.6 volts. V2 is 1.8 volts, and V3 is 6 volts. So if you notice, all the numerical calculations have been applied to each calculated quantity. Always remember that a quantity without a unit of measurement is, is meaningless. You have to have units. Units are critical. Okay, without units, the quantity don't mean anything. Okay. Another important thing to go back to what we already said is that, remember how we said that the largest resistance is the one that has the most impact in the total circuit? And that's another way of looking at this here. If you look at this circuit, the largest resistor was 100 ohms, so the largest voltage drop happens across that 100 ohm resistance. So this has the largest effect. Okay, the greatest voltage drop happened across resistor R3, and it's equal to 6 volts. Another example here, it says, first of all, find total resistance in the circuit. Okay, then using that value, calculate the source current rather, and then find the individual voltage drop across each of the resistors. So this is the same thing we did before, but all put together under one example. So to calculate the total resistance, I first need to know, first calculate the source current. I first need to know the total resistance, okay? Because I cannot know the current unless I know the total resistance for this particular case. So the total resistance, since they're in series, is simply going to be the addition of the three resistors, 2 plus 1 plus 5. Or 8 ohms. So now from Ohm's law, the total or the source current is equal to 20, the voltage, divided by the resistance total, or 2.5 amps. So 2.5 amps, and remember, is what's coming out of the source. And the same 2.5 amps is what's going through R1, through R2, through R3, back to the source. Okay, it's the same current. So using what we already used before, Ohm's law, I can calculate the individual voltage drops by simply multiplying the current times the individual resistance, and that's what I've done here. 2.5 times 2, 2.5 times 1, 2.5 times 5, and that gives me the individual voltage drops. So if I put a meter across V1 and measure voltage, I will measure 5 volts. and so forth for the other ones. This is another case. In this case, we have 4 resistors in series, but we happen to have 3 resistors that are the same, they're equal, so we can use that simple rule, and I can just take 3 times 7 to calculate the total resistance, or the resistance for those 3 resistors together will be 21, right? 3 times 7, and add this other resistor 4 to get the total resistance, which will give me 25. Right? 3 times 7 plus 4 will give me 25, and that's the total resistance. And I also want to know, in this case, the current coming out of the source. So again, current coming out of the source will be equal to the voltage, which in this case is 50, divided by the resistance, which is 25, which will give me 2 amps. Right, 2 amps, 50 divided by 25, and then the last question was find the voltage across resistor R2. That's the only one they're looking for, and indicate its polarity. Notice here that they label the polarity in this fashion, see? And if you notice, something that we didn't really point out at the beginning of the problem, this battery is connected positive toward ground and negative towards the other side of the circuit, right? So positive is connected to ground in this case. It doesn't change a lot of things, okay, that we already know. It doesn't change our theory. The only thing we gotta be aware of is the direction of the current flow. Since, again, conventional current flow leaves the positive terminal, then in this case, the current is gonna flow in this direction, see? Conventional current flow is gonna flow in that direction, okay? Because remember, the polarity will tell you the direction of the current. Okay, so don't get confused by that. So that means that if the current is going counterclockwise, then this voltage drop happens with the positive terminal on this side and the negative terminal on that side. So they want to know what's the voltage across the resistance and indicate the polarity on the circuit. So we know the polarity because of the current flow, right? Remember what I showed you before. If you know the direction of the current, you should know the polarity across the resistance, right? So in this case, it's not going to change the value per se of the voltage, because that's still going to be 2 times the current times the value of the resistance, which is 4 ohms. So the voltage drop is 8 volts. Okay. All right. Let's look at another example, a little different here. But it's just reusing what we already know. In this case, we have 3 resistors connected in series, okay? R1, R2, and R3. And what we know here is that we know the value R2, we know the value R3. They're giving us the value of the current flowing through the circuit, but we don't know the value of the source voltage. And we don't know we do know the value of the total resistance. Okay, so it's a little different, right? So what they want to know is what's the value of R1 and what is the value of the source voltage in this case? Well, given what we know already, we can easily find those values, because what we know is, without knowing any numbers, without plugging in any numbers, is that the total resistance is equal to R1 plus R2 plus R3, right? We know that. And we know our total, and we know R2, and we know R3. So the only unknown is R1. So if we apply that idea, that equation, RT is equal to R2 plus R1 plus R3, we can solve for R1, because that's the only unknown here you can see in this equation, right? We know the total resistance, we know R2 and R3, we can solve for R1. So if we solve for R1, gives us 2 kilo ohms. Very easy to check. If we plug in 2K into this expression, we obviously are gonna get 12 kilo ohms, right? So, and then since we know the value of the total resistance and we know the value of the current, we can easily find the value of the voltage at the source using Ohm's law. which is simply the value of the current times the total resistance, 6 times 12, or 72 volts. All right, so make sure you are understanding those problems, review them, make sure you get the same numbers, and make sure you're understanding. We're going to do some more of this stuff later in the lab, where we actually going to be measuring voltages using the meters, in this case digital multimeters. When you measure voltage, something to remember is that when you measure voltage the same way you measure resistance. And what I mean by that is that you measure across. Okay, see how the meter is placed across the element, across R1, across R2, across R3. When you measure resistance, you would put the meter in the ohm meter mode, and you will turn the source off, remember, to measure resistance. And that will give you resistance. And if you wanted then to measure voltage, you wouldn't have to change the connection points. Okay, all you have to do is put the source back on and move the your selector to voltage, to DC voltage, and then you will measure voltage. Positive work with the positive, of the polarity of the voltage across the resistor, and negative also, the negative lead to the negative of the voltage drop across the resistance. If we swap that, then you will get a negative value. Okay, and again, we'll do some of this in the lab so you have a better understanding. Another thing you're gonna learn also later is that, as I showed you just now, when you measure resistance or voltage, as you notice, you're not breaking anything. By breaking anything, I mean you're not disconnecting anything in the circuit. When you measure current, however, and remember this, even if it doesn't make sense at this point, when you measure current, you will have to break the circuit. You will have to break the connection. Okay. Another way of saying this is that when you measure voltage or resistance, you put the meter across the element. See? Or you can say also you put the leads in parallel with the element you're measuring. See? In parallel, right? Across. Then when you measure resistance, you put the meter in series with what you're trying to measure. So again, even if it doesn't make sense at this point, remember that concept and you will see how easy it is to do in the lab environment. And this is what I was saying before. Notice the difference. I'm measuring voltage, right? See how the leads are connected in parallel across the elements, right? But if I measure current, I broke the circuit, right? I actually opened two ends and connected back through the meter, see? Through the meter. In other words, I'm placing the meter in series with the elements that I want to measure, see? In series, right? They follow the path with the meter. This is very, very important in the lab environment, very crucial, okay? All right, so now, so now let's look at power distribution in a series circuit. If you need to review the equations for power, I'll recommend that you do that first, because you need to be really familiar with power before we continue on. But the equations, remember, are very simple to finding power. There we have about 4 equations at least that we know of to find the values for power. So make sure you review that before we continue, if you need to. But when we have elements in series, like the resistors we have been looking at so far, nothing really changed in terms of power, in terms of using the equations that we already know. It's just expanding what we already know for the use of the concept in series connected circuits. So the power applied by the DC supply must be equal to the power dissipated by the individual resistor elements. And that's, that's coming from conservation of energy, right? Energy supply should be equal to the energy expend by the devices. So the power supplied by this battery in this case is going to be equal to the sum of the individual powers absorbed by each of those resistors. Resistors, remember, absorb power. Okay, a source could provide power or could absorb power depending on the type of source, but resistors always absorb power. Okay, when we say absorb, they do absorb power in terms of heat, in terms of light, right? Every time you see, like a light bulb, every time the light bulb heats up, it's absorbing power. The power providing light, it's absorbing power. So what we said again is that the total power being supplied by the source is going to be equal to the individual power absorbed by the resistors. Another way of looking at that is that the total power delivered by the supply is also found by Ohm's, or by the concept really of power, the basic concept of power, right, is the product of the voltage and the current, remember? So in this case, the power supplied by this source is going to be equal to the voltage supplied by the source times the source current, or the current coming out of the source. So the power supply is the product of this voltage times this current here. So that's what this equation is, right? And if we use some of the other equations that we know from Ohm's law, then we can also find the individual power absorbed by each of the resistors. And that can be found, again, this individual power is going to be equal to the voltage times the current through the resistor, the voltage drop times the current through that resistor, the voltage drop times the current through that resistor, right? Which is what this is. Or we can use any of the other equations that we know if we know the current or if we know the voltage. Same thing applies. So in a series configuration, maximum power is going to be delivered to the largest resistor. The largest resistor will get the maximum power. And again, you can see that from those equations here. So let's look at some examples. We have a series connected circuit here. We have 3 resistors connected in series. They're all connected to the source. So we should say that all the elements are connected in series. That's something you should understand by now. The battery and the 3 resistors are all connected in series, right? It's one single string, if you will, right? And they all close a path. So in this case, we want to know, first we want to know the total resistance. So the total resistance, again, like we know before, is going to be the addition of the 3 resistors, 3 plus 1 plus 2, or 6 kiloohms. Very easy. And then the source current, by Ohm's law, is also going to be found by dividing this voltage supply by the total resistance, or 36 into 6, which will give us 6 milliamps. They also want to know the voltage across each of the resistors. So the voltage V1, V2, and V3 across each of the resistors by Ohm's law is simply the current times the resistance, right? So the current we already found out is 6 milliamps. So this voltage drop is 6 times 1. This one is 6 times 3. And this one is 6 times 2, which give us 6 volts, 18 volts, and 12 volts. All right? Make sure you can get these 3 results here. Now for the power, they want to know the power supplied by the battery. Well, by the equation we already described previously, right? The power supplied by the source is going to be equal to the voltage supplied by the source times the current coming out of the source. We already found that the current coming out of the source is 6 milliamps. So the power supplied by the source, or in other words, saying the power delivered by the source, is equal to 36 volts times 6 milliamps, or 216 milliwatts. Okay. And the next thing we want to know is the power absorbed by each resistor, or dissipated, another way of saying absorbed or dissipated is the same thing. The power dissipated by the resistance is going to be equal to, if we can use any of the equations. So in this case, they're going to do for P1, they're going to use the voltage times the current. So the voltage across P1, we already know is 6 volts. The current is already 6 milliamps, so it's just 36 milliwatts. We can use the same equations. It doesn't matter. We have all these choices, remember? But just to show you how to use the other ones, they're using current in this case for P2. So it'll be the square of the current through R2 times R2. Use as 180 milliwatts. And for the power absorbed by resistor 3, or dissipated by resistor 3, is going to be the voltage across resistor 3 square over the resistance. In this case, the voltage across R3 is 12 volts. So 12 square over 2 will give us 72 milliwatts. And so the last thing is, well, you know, what happens when you compare the total power supply to the power dissipated by the individual resistances? Well, by conservation of energy, the power supply has to be equal to the addition of the individual power absorbed or dissipated by each of the resistors. And so this individual power absorbed by each resistor, 36 plus 108 plus 72 milliwatts, has to be equal to the total power being supplied by the source, which is 260 milliwatts. All right. The next topic is voltage sources in series. Voltage sources in series can also be combined. Just like we combine resistors, we could combine resistors, we can also combine voltage sources when they're connected in series, if we need to do so. For example, all you have to do is follow the polarity, right? Be careful that you follow the polarity. For example, in this case, if you want to know, like if I put a meter from the top end and the other side of the, one side of the lead, or one lead to the top, another lead to the bottom, and measure the voltage from top to bottom, then what voltage would I will measure? Well, since if you look, for example, at the polarities of the voltage and how they're connected in series, right? Because they have one connecting point in common. E1 and E2 has one connecting point, E2 and E3 has one connecting point. And they're all connected positive to negative, positive to negative, positive to negative, right? So they all add up together. So when you put a meter from the top to the bottom, you're going to measure 18 volts, 10 plus 6 plus 2. One way of looking at this is if you walk, let's say, from top, let's start from the bottom. If you walk from bottom to top, right, you will go negative, positive. So you'll have a gain of 2 volts, right? A gain, because you're gaining 2 volts, meaning that the potential at this point is, or rather, the potential at this point is 2 volts higher than the potential at this point. Same thing for the other one. The potential at this point is 6 volts higher than at this point. The potential at this point is 10 volts higher than at this point. Now, notice again that all of this is relative, right, to your point of view. Remember that concept again I gave you of the two hills, two points in two different hills. One is taller than the other one, right? If you're A looking into B, you're taller than B. But if you at B looking into A, you're shorter than A, right? But where you are doesn't change, right? You're just either higher than one point or lower than the other point. The same idea here. So as I go from the bottom to the top, you gain 2 volts in this direction, then you gain 6 volts in that direction, then you gain 10 volts in that direction. So the total gain is 18 volts, see? So these 3 batteries connected in series are equivalent to this single 18-volt battery with the polarity as shown. Very important. If you notice in this other example, the polarities have changed the way they're connected. So again, if I go from top to bottom, and this also works from bottom to top, by the way, okay? The other way around. So if I go from bottom to top, just like I did in the previous example, I have a gain of 4 here. And then I have a drop of 3, see? Because I go from positive to negative, I drop 3 volts. And then as I go up to the top, I have another drop rather of 9 volts. So I have a gain of 4, a drop of 3, and a drop of 9. So I go 4 minus 3 minus 9, right? So minus 3 minus 9 is minus 12, plus 4 is 8. So you have a total of 8 volts with the polarity indicated. So see how the polarity is indicated here, because the total polarity from this point to that point is going to be positive with the to the ground. And so also notice the direction of the current. Everything checks, because the current in either case follows our convention or conventional current flow. All right, so make sure you understand these examples here. All right, and this is something that you've typically done before. That's sort of connection, like when you connect batteries to a remote control or a flashlight or anything like that, right? You always go positive, negative, something like this, right? It's the same idea here. By doing that, the total voltage becomes larger. See? If you miss one of those connections, and you've probably done it before without realizing you connect one of the batteries the wrong way, what happens? Well, the device won't work. The remote won't work, the flashlight won't light up, or something, right? Something will not work unless you connect it the right way. So doing that allows you to go, and again, look at this connection, right? It's also a series connection, okay? And you can tell that by following the path. It's a single path, single string, and you have the two of the batteries connecting to a single point. These two are connected to a single point. These two are connected on a single point. These two are connected by a single point. They're in series, right? So if I go from left to right, started here, I go 1.5 volts, 1.5 volts, 1.5 volts, 1.5 volts, right? So you have a total of 4 times 1.5 will give you 6 volts. See, it's the same thing we did here, right? The same thing. The total is 6 volts. So connecting batteries or sources in series allow you to, increase the voltage if you need to, or decrease the voltage if you need to your for your purpose. And we'll do some of this in the lab later when you do some of the connections like this. So remember, you can always combine sources, batteries in series with no problem. The only thing is that you gotta be careful when you follow the polarity. You gotta be careful with the polarity, okay? All right, so this brings us to what's called Kirchhoff's voltage law, and it's normally just referred to it as KVL. And KVL is going to be very useful for us to analyze circuits, especially when circuits are connected in series. So we're going to start by saying that if you look at a circuit like this, right, where you have 2 resistors connected in series to a source, right? We know that already. Kirchhoff's voltage law, and again, the important thing is you have a closed loop, right? This is a loop. It's a loop connection, right? It's connected from one end to the other one. It's a closed circuit. And it says the algebraic sum of the potential rises and drops around a closed path or a closed loop is always equal to 0. It sounds complicated, but it's not. And what it means is this, right? Let's start at point D, for example. And let's go from D to A to B to C back to D. So we're going to go clockwise, right? Starting from D. If I start at D towards A, I have a voltage gain, don't I? right? Because I'm gaining voltage as I go from D to A. I'm going negative to positive. As I go from A to B, I have a voltage drop of V1, right? The voltage drops. As I go from B to C, I have another voltage drop from B to C, don't I? So what KVL says, what Kirchhoff's law says is that, and then I go back to D, right? There's nothing between C and D. It's the same potential. There's no drops. So what KVL says, what Kirchhoff's voltage law says, is that if I add all the voltages algebraically means that I'm taking the signs into account. Okay, that's what algebraic sum means. So if I go from D to A, I have a voltage gain, and then I have 2 voltage drops, right? So that means that if I add this voltage gain and I add these 2 voltage drops, the result is going to be equal to 0. And this is what this means. The sigma letter indicates sum, uppercase sigma indicates sum of the voltages. This little arrow indicates around a closed loop. All right. So remember what we just did, right? I went from D to A to B to C back to D. It's a closed loop. And as I go from D back to D, I'm looking at all the voltages. Some of those are gains, some of those are drops, depending on the polarity. The voltage from D to A is a gain. The voltage from A to B is a drop. From B to C is another drop. So the sum of all the voltages, the algebraic sum, meaning I'm taking the signs into account, is going to be equal to 0. Now, the rule applies in any direction, okay? But you always have to pick a direction and stick with that direction until you close the loop. What I mean by that is that, well, in the example that I just showed you, I was going clockwise, right? D, A, B, C, D. What if I go the other way around, counterclockwise, D, C, B, A, back to D, this way? Well, from D to C, there's no voltage drop, right? There's nothing there. From C to B, see what happens now. From C to B, now I have a voltage gain, right? See, everything is relative. That's what's important, that you always know where you are, because this is relative. So from C to B, going in that direction, I see a gain now. From B to A, I see another gain. And from A to D, I see a drop now. Okay? But what matters is that if I go in that direction and I add the voltages according to Kirchhoff's voltage law, it's going to be the same thing. It says that if I add the voltages around the loop in either direction, the voltages are going to add up to 0. Okay? All right. So it may sound complicated, but you'll see how examples will show that this is not as complicated as it sounds. Another way of stating Kirchhoff's voltage law is also saying, well, if you look at a circuit like this, and if you look at the closed loop, and if you add up all the voltage rises or voltage gain, same thing, rise, gain, if you add up all the voltage rises and on one side and put all the voltage drops on the other side, they both should be equal. And that what this is saying is this: the sum of all the voltage rises is going to be equal to the sum of all the voltage drops around a loop. It's the same thing, and you'll see why when we look at one example. So let's look at this example, right? Now we have 2 sources, and the 2 sources are connected to 2 resistors. The whole circuit is connected in series. I hope you realize that by now. Physically, you can tell. It's easy to say that they're connected in series. So if I start, I'm going to start by, and remember, as long as you're consistent, I can go in any direction. I can go clockwise, or I can go counterclockwise. In either case, the results should be the same. That's the important thing to remember. Okay, so if I go from ground in a clockwise direction, right? The first thing I'm going to have, and I'm going to use this equation first, this one, the general form, right? The algebraic sum of all the voltages around the loop is equal to 0. So if I go from ground to this point, I have a voltage gain, right? 16 volts. So I'm gonna put all my voltage gains as positive. Okay, the convention. Okay, I'm gonna just assume my voltage gains are positive. It's like if I continue across R1, I have a voltage drop of V1. So I'm gonna write my voltage drops as negative. So this is my voltage drop. And then I have another voltage drop here across R2, and I'm gonna draw that again, or put that again as negative. And then as I continue, notice here that I have another source. By going in this direction, this source looks like a drop now, right? So I have a drop now of V2. So all the algebraic sum of all the voltages, right? The gain and the 3 drops should be equal to 0. That's what KVL says, okay? And that's all I'm following. I'm just following the polarity to tell me where the gains are or where the drops are, or the rises for the gain is the same thing. So in this case, right, if I do that, look, this equation, right, you maybe want to just practice again and make sure you get it. Then the only unknown is, since I already know the 2 source voltages and this voltage drop, I can simply solve for V1. So V1 happens to be 2.8. So this shows you that you also don't need to know the values of the resistors or the current if you want to know an unknown voltage in this case, for example. If you know the other voltages, then you can use Ohm's law to calculate that those voltages. All right. So now, where are we? Okay. All right. Notice also that I could also gotten the same result if I add the voltage drops equal to the voltage gains, right? Again, if I go in this direction, I have a gain of 16, right? So that's the only gain I have, right? And if I put the gains on the left, doesn't matter where you put them, but if you put them on the left, in this case, I only have one gain of 16, and the other 3 will be voltage drops. And if I add the 3 voltage drops on the right-hand side of the equation, which is this case, it's the same thing, I'll get the same result, because all I'm doing is I'm moving all the 3 drops to the right-hand side, and I get the same result, right? This one. So this is the other form of the equation, right? It's just the same equation as this one. It's the same thing. It's just moving things from one side of the equation to the other one. It doesn't change the result, but it's a nice point of view, because sometimes it may be simpler to look at the equation this way. Okay. Let's look at another example here. It says, find the voltage Vx in this circuit. How do we find that? Well, think about it this way. What will happen if you put a meter from this point to that point? What will the meter measure in terms of voltage? Okay. Well, it will really measure the voltage on either side, right? Meaning that the voltage that you will measure will be the voltage from this point across R1 across the source. That's the voltage it will measure. But it will also measure the voltage across R2 and R3. It's the same voltage, right? It's the same voltage because it's the same 2 points related to the circuit. So if I want to use Kirchhoff's law to figure that out, again, I can start by, since the only thing I want is this voltage, right? I can start again if I start from, and again, you don't always have to start at the bottom or from ground. You can start anywhere, okay? That's the nice thing about this law. And you should practice any other starting from any other point, and the numbers should check back again accurately. But let's just say you start again at the bottom here from ground and then go clockwise. So again, I'm going to have a gain of 32 across the source, right? This is my gain here. And I'm going to have a drop as I continue across R1 of 12 volts. This is the drop across R1. And as I go down this way, right, because this is the voltage I want, this is Vx, I'm closing my loop. See, I close my loop here. Then that voltage Vx is also a drop. So I have a gain, a drop, and a drop. A gain, a drop, and a drop, right? And all I have to do is add up the numbers. If I solve for Vx in this equation, it'll be equal to 32 minus V1, or 20 volts. Okay. If I do the same thing on the right-hand side path, right? If instead I'm going to use this portion of the circuit, I can do the same thing. If I start at the bottom here and go up through Vx is a gain, and then I have a drop of 6 and a drop of 14. See? Is this equation right here. A gain for Vx going clockwise, and a drop for V2 and a drop for V3. So solving for Vx, I should get the same thing, which is 20 volts, and it should be the same. Because like we said before, the voltages are the same. Okay? All right. Let's look at another one. This is figure 529. It's a combination of voltage sources. Okay. And what we have here is, okay, if we're using KVL, we want to find out the voltage V1 and V2. V1 is from these 2 points, and V2 is across these 2 points. Okay. So if we start with path 1 here, right, if we go clockwise, right, and start at A, you have a gain of 25. You'll have a drop of V1. This is assuming you put a meter here, right? The meter will be measuring that voltage. You have a drop of V1, and then going back this way, you have a gain of 15 back to A. See, A to this point, back to A. It's a closed path, and at every point, I'm looking at the voltage rises or the voltage drops. So I have a rise of 25, I have a drop of V1, and I have another rise or gain of 15. So the solving for V1 gives me a voltage for V1 of 40 volts. See, 40 volts. So what that means, if you look at this carefully, right, is that the difference, what this is telling you is that the difference from this point at V1 to this point at V1, these 2 points, the difference or the voltage is 40 volts. There's a 40-volt difference, right? And you can tell that by looking at the results of the equation, right? Now, for the second path, if we start at point A again in a clockwise direction, right, I'm going to start at A again in the clockwise direction. So I'm going to go A, there's nothing here, so I have a drop of V2 and another drop of 20 volts back to A. See? Right? This way, in the clockwise direction. A, nothing, drop of V2, a drop of 20, back to A. And then obviously then, again, 2 drops, right? Drop of V2, drop of 20. If I solve for V2, the result is minus 20 volts. And the minus sign indicates that the actual polarities are different than the ones you assume. If, in other words, if you get, if they tell you, for example, measure the voltage across V2, they're not going to tell you where the polarities are, right? But if you assume, let's say you take your meter and put the positive lead here and the negative lead here, and the result is negative, it says, oh, wait a minute, It's the other way around. The negative result tells you that you put the leads in the wrong place. That's all it's saying. You can correct yourself. The value of voltage is the same. It's just the polarity that's going to be different, right? Because again, assuming again that they don't tell you, like in this example, they indicated the polarities. But if you didn't know the polarities and you measure in this way with the positive lead here and the negative lead here, and the result is negative, it just means that the actual polarity is different from the one you assume. Okay, no problem. All right, a couple of examples. This one, using Kirchhoff voltage law to find the voltage for the circuit in this figure. And again, in this case, the unknown is V of X. And we can use what we already know about KVL. So we're going to start again. I don't want you to get the idea that you should always start from the ground. You can start from any point, okay? But let's just assume we start from the ground here and go up clockwise. So I have a gain of 16 volts, a drop of 40, a drop of Vx, and a gain of 30 volts. And this is represented by this equation. They all should be equal to 0 by KVL. So 60 minus 40 minus Vx plus 30 equals 0 volts. And then I just solve for Vx. Right? The rest is just a simple equation. So Vx is 50 volts. Let's see, another one here, 512 says find the voltage for the circuit in this figure. We're looking for Vx. Again, it's a closed path. Remember, not all circuits are going to look nice or square or rectangular all the time. You can look differently. But in this case, if you start from ground again, if you want, and I'm just following the solution they have here. Okay, that's why I'm following this direction. But I can start at any point. And I encourage you to start at any point, at B and go clockwise, at B and go counterclockwise, anywhere, start anywhere, and you should get the same results as long as you're consistent with the polarities. All right, so let's start with this ground and go up towards the right. Clockwise. So I'm going to have a drop of 6 volts, another drop of 14 volts, and I'm going to assume, see, they don't give you the polarity of Vx, see? You don't know that, right? So I'm just going to assume it's another drop, and if it is a drop, indeed, the result is going to be positive, see? It actually corrects it corrects yourself, if you will, if it's not the actual polarity. So in this case, they don't tell you what the polarity of Vx is. So I'm going to assume it's positive from A to B, and B is negative, right? And if it's not, remember, if Vx happens to be negative, that means that I assume the wrong polarity. No problem. You just make the correction. So let's start again. From ground, I have a 6-volt drop. And I have another drop of 14, another drop of Vx, and going back to this ground point, I have a gain of 2. And this is this equation. So by this point, you should be able to get this equation. All right, practice it. Make sure, maybe on your own, write it on a different piece of paper, and make sure you get this equation with these signs like they are if you're going the same direction I went clockwise, right? So as you can see now, the only unknown is V of X. Now, if I solve for V of X, look what I got, minus 18 volts. Well, what that tells me is that, okay, I assume there was a drop from A to B, but actually it was a gain, not a drop. Okay? All right, so that's all you gotta correct. And if you make that correction, you'll see that everything checks in here for this equation. Okay? All right, let's see how many more examples we got. We got one more. Let's do, let's just do 513. And I'm going to leave you to try 514 on your own. It's right there. So 513 says, if you look at this figure 532, we want to find V2 using KVL. And we want to know the current I2. And we want to know the values of R1 and R2. how do I start this? Well, when you and you can already see that things are getting a little more complicated because there are more things you need to find out and there's more information you have. But if you're organized, this is where you got to start getting really very well organized. If you're not well organized, you're going to have a lot of trouble analyzing, finding values in the circuit. So try to be very organized, okay? Start by maybe writing out what they're giving you, writing out what you want to find out, writing out the equations you know that can help you find out what they're looking for, okay? In this case, it says, find the value of V2. And let's see, they're giving me, what are they giving me here? They're giving me the source voltage. They're giving me the voltage drop across R3. They're giving me the voltage drop across R1. They're not giving me the voltage drop across R2, which is what I'm looking for. But they're also giving me the values of resistance R2. Notice that they're not giving you the values of resistance R1 or R3, right? So again, you see what's going on here. Now, based on the circuit, you can tell the direction of the current, right? Because look at how it is connected. The positive is connected to ground, so the current is flowing in the direction is shown in the circuit, right? No question about that. And that's why I know the polarities here, right? Because if I'm following the direction of the current, then the polarity should be this way, right? And that's why it's important to remember to associate current direction with polarity or polarity with voltage direction. It's got to check. So far, you know, that's what I'm given. So what are the things that I can use immediately that can give me something here? Because I'm missing things. Well, you know, I know one thing, right? I know that KVL says that the voltage drops across the closed path are going to be equal to the voltage gains, right? Or say another way, that is that the sum of the voltages, the algebraic sum of the voltages around a closed loop are going to be equal to 0. So I can apply that rule again, and if I do that, what will that give me is something that I already did in the previous two examples. I will get the value for V2. Because if you start at the ground level and go clockwise, I have a drop of 54, I have a gain of 15, I have another gain of V2, and I have another gain of 18, and that gives me an equation with a single unknown, V2. See? Very simple, right? Now, if I know, and this is, by the way, another way that you can encourage you rather, to exercise this concept is that you kind of solve the problem by wording it the way I'm doing it now, without even putting numbers, without even solving for numbers. But if you learn to start doing that, it gives you another way of looking at the problems without complicating it with the numbers, if that makes sense. Because that's going to steer you to the right solution. So again, let me tell you what I did again. It says, well, you know, I have these unknowns. I have V2 is an unknown, R3 is an unknown, R1 is an unknown, and I2 is also an unknown, right? But if I use KVL, I can immediately solve for V2, right? Because I add all the voltages and the only unknown will be V2. And look, once I know V2, can I find the current? Yeah, if I use Ohm's law, because the current through the circuit is the same, and if I use Ohm's law, then I know that, because I know the voltage already, right? It's going to be this voltage that I just found out divided by 7. That gives me this current, right? And now look at this side. If I know the current, which I already found out is for I2, using Ohm's law, I can solve for R3. Same thing here. Using Ohm's law, I can solve for R1. So, point again is that even without me solving for a specific number, I already know how to solve the problem. You notice that, right? If you get used to doing that, I can guarantee you it's going to be a lot simpler for you to solve problems like this. So again, let's look at the solution. So again, what I did was I went around the loop and solved for V2 using KVL, right? We saw that. And this is this equation. So if I solve for V2, it gives me immediately 21 volts. And then I'll do what I just said before to find I2, since I already know this voltage. It's just Ohm's law. It'll be V2 divided by 7. 21 divided into 7 gives me 3 amps. And since I already know the current is 3 amps throughout the circuit, right? I can simply solve for R3 here and for R1 here using Ohm's law. So R1 will be 18 into 3, R3 will be 15 into 3, and that gives me the values for the resistors. And I'm going to leave this one for you to try it and to practice. All right, I'm going to stop right here, and we're going to look at this next very important, excuse me, a really, really very important concept here. This is called voltage division. That is very, very useful for solving circuits. But I'm going to leave that one for the second part of this chapter.